semiconductor nano devices, manufacturing technology in mechanical, electrical, electronics, and chemical engineering, and electrical and electronic material engineering. And their team, their lab, in the lab, they are developing the technologies for manipulating single charges, spins, and phonons in silicon in the Device Physics Laboratory, Research Institute of Electronics. And Professor Ono is a recipient of many awards. And to name a few, he has received Takayanagi Memorial Award, Ministry of Education, Culture, Sports, Science and Technology, Japan, Awards for Science and Technology, and Japan Society of Applied Physics Silicon Technology Division has conferred with Silicon Technology Division Paper Award. Japan Society of Applied Physics in 38 JSP he's received award, and recently in the year 2020 or 2021 he's got many memorial symposium award. He's given plenary talks in Takayanagi Memorial Symposium, and has published many papers in applied physics, physical review, applied physics letters, and so on. So I have great pleasure in introducing such a personality to this session. We welcome you, sir, to request you to deliver your talk.
Okay.
Professor Ono Yukinori, you can share your screen and you can start your presentation.
Okay. Can you see my slides?
Yes, yes, you can see your slide.
Okay. Thank you very much for the kind introduction. My name is Yukinori Ono, Research Institute of Electronics, Shizuoka University. So today I'm going to talking about electron-electron scattering in silicon and its impact on future emerging devices. So this is an outline of my talk. First, as an introduction, I'd like to introduce a new device that we have recently developed, and we call it the electron aspirator. That is based on the electron hydrodynamics, or based on electron-electron interaction or scattering. Then I'd like to show you the detail of the experiments about this new device, including device structure, fabrication process, and the measurement results. And then I'd like to give you some analysis. At first, I'd like to explain that there is some fundamental limit of the energy dissipation in field effect transistor. And then I'll explain that the electron aspirator can overcome this fundamental limit. And for this, I make a brief review about the scattering process in electronic devices. And finally, I'd like to summarize my talk and make some acknowledgements. So let me first introduce the aspirator, conventional aspirator. As you may know, the aspirator consists of 3 terminals, water inlet, outlet, and suction head. So if we connect the suction head with the pressure gauge and introduce a strong stream of water from the water inlet, then the pressure decreases. This effect is called the Bernoulli pumping effect in hydrodynamics. Therefore, if we connect the suction head with a tank, some liquid can be pumped to the outlet together with inlet water. So the physics behind this operation is the internal particle-particle collision taking place here. And the significant point of this device from the viewpoint of the application is that we need no power for this pumping procedure. Therefore, this is conveniently used in the laboratory for example, of chemistry. And so the aspirator is sometimes called the Z pump. So what we have fabricated is the electronic version of the aspirator. So we use the highly scaled MOSFET for the high energy electron injection. Then we can generate a net current flow between the two grounded terminals, which are called base and collector. The physics behind this operation is the internal electron scattering taking place here. And similar to the conventional aspirator, the no power supply is required for this pumping operation, which means that this device is quite energy efficient current amplifier. So what we have done is that we fabricated the electron aspirator using nanoscale silicon MOSFET and demonstrated the amplification of the transistor current by a factor of 3 at a low temperature of 8 Kelvin. And these results are already published in these articles. And the significant point of this achievement is that this is the first silicon nano device based on electron hydrodynamics. The another important point is that this device could break the fundamental limit of the MOSFET drivability, which is tightly related to the energy dissipation issue of the electronic devices. So next, I'd like to explain the experimental detail on this electron aspirator. So this is an SEM image, top view of the device, comprising the emitter, collector, and base. The size is about 200 nanometers. So this is the schematic magnified view of this core area of the device. This is a top view, and this is a cross-sectional view. And actually, the device was fabricated on the so-called silicon insulator substrate, or SY substrate. And so the gray region corresponds to the silicon. And the width is about 30 nanometers. And these blue area correspond to these fine gates, which we call the emitter and the collector gate. The spacing between these two gates is about 90 nanometers. And as you can see, the whole area is covered by the broad gate, which we call the upper gate. And by applying the positive bias to this upper gate, the region here and here and here, we can generate a two-dimensional electron gas, which act as an electrical lead for this fine gate transistors. One of the important points for the fabrication is that we used a very clean silicon SOI layer with no impurities. This is because in order to observe the hydrodynamic effect, or in order to make the electron-electron scattering effective, the unwanted impurity scattering has to be eliminated. That's why we use the very clean silicon layers. So next, I'd like to explain the fabrication process of this device. This is a bird's-eye view. We start with the preparation of the silicon insulator layer within the top silicon layer down to about 20 nanometers. Then we define the emitter, collector, and the base terminals by using the electron lithography. And next, we form the thermal oxide on top. Then we define the fine gates, emitter and the collector gates, which are made of polysilicon. Next, we deposited the SiO2 silicon dioxide film layer. And finally, we define the broad upper gate. Okay, next I'd like to explain the measurement setup. Because the measurement procedure is very complicated, I'd like to explain the procedure in relative detail. So first, we make the base and the collector terminals grounded, like this. Then we introduce the electrical current of 10 nanoamp from the emitter to this T-branch region. The energy of this incident electron is controlled by the voltage to the emitter, and the current level, it can be controlled by this emitter gate voltage. Then we sweep the collector gate voltage like this in order to control the barrier at the collector. Then we measure the current of base and the collector. Then we made a similar, the same measurement by changing the energy of the incident electrons, like this. So let me show you some measurement results. Those measurements were done at 8 Kelvin. First, I'd like to show you what happens if this energy is very small. And these are the data of emitter current, base current, and the collector current as a function of the collector gate voltage, which is this. And as I explained, the emitter current was kept constant at 10 nanoamp. Then, when the collector gate voltage is below the threshold, we have the large barrier here, so that all the electron goes to the base. Therefore, the current, base current reaches 10 nanoamp, which is the same as the emitter current, and the collector current is 0. However, when we reduce the barrier height, then the electrons are allowed to drain to the collector. Therefore, the base current is reduced down to 5 nanoamp, and the collector current increases to 5 nanoamp. This means that in this case, the electrical current is quite normal. Both base and the collector have similar current levels. However, if we increase the incident energy, the characteristics was found to dramatically change, which I'll show you next. So again, when the collector gate voltage is below the threshold, all the electron goes to the base, like this. However, when we reduce the barrier, the polarity of the base current is reversed, and the collector current increases and becomes larger than the emitter current level. This is actually the operation of the electron aspirator. Actually, we can generate the electrical current between two grounded terminals, which is in effect the aspirator pumping effect. So we can define the current enhancement factor, Ri, which is given by the collector current divided by the emitter current. And as I explained, the emitter current was kept constant. Therefore, the enhancement factor characteristics is completely the same as the collector current characteristics, like this. And you can see that the current enhancement factor reaches 3 at maximum. And I'd like to skip the detail of the mechanisms of this peak structure. But at this voltage condition, there is a small hump remains here underneath the collector gate voltage, collector gate. So this small hump prevents the backflow of electron from the collector to the T-branch region. In other words, the collector gate acts as a check valve of the aspirator, of electron aspirator. And I'd like to show you one more experimental result, which is more important. So we operated this device in 2 different modes. One is transistor mode, the other is aspirator mode. So in transistor mode, we bias the base so that the current becomes zero. So in this case, this is simple two-terminal device. And if we operate this device with the emitter gate, this is a simple MOSFET structure with source and drain. On the other hand, in aspirator mode, we allow electron to flow through the base by making the base ground. So, and then we compare the current characteristics between these two modes. And this is output current as a function of the main gate voltage, which is the voltage to this emitter gate. And this is the current characteristics with the transistor mode. Of course, the input and output currents are the same. On the other hand, in the aspirator mode, we really observe the reverse current flowing between the base and the collector. And as a result of this reverse current, the output current becomes larger than the input current, which corresponds to the amplification of the input current without any additional voltage source. This means that the electron aspirator is quite energy efficient current amplifier. So in order to make a deep understanding of this operation, I will make some analysis. And first, I'd like to show why we have a fundamental limit of the energy dissipation in MOSFETs. So this is a MOSFET structure, and this is a band diagram when we apply the drain voltage to the drain. And when the MOSFET is highly scaled, injected to the channel, travels the channel nearly ballistically. However, in MOSFET, the energy is unavoidably dissipated. And I'd like to show you what happens. So, as you know, the injected electron gains the energy from the electric field, given by this equation. However, this additional energy is dissipated to the phonon bus at the drain edge. And finally, the electron's energy goes back to the initial value. This means that, and this energy dissipation is unavoidable in field effect transistor. On the other hand, in electron aspirator, the energy gained from the electric field can be transferred to the other electrons before it is dissipated to the phonon bus, which means that the electron aspirator can use the energy EVD, which otherwise unavoidably dissipated in a transistor. So in this case, the enhancement factor Ri is given by this simple equation, the square root of EVD divided by the Fermi energy, which come to about 6 in this experimental condition. And as I explained, the experimental data shows that the maximum enhancement factor was about 3. So this means that we have still some room for the improvement of the device performance. But in summary, the electron aspirator is an energy efficient amplifier beyond the fundamental limit of the transistor. And finally, I'd like to explain what happens in a device where the electron-electron scattering play a dominant role. So suppose that a hot electron collides with a cold electron, then scattering happens. However, in this process, the total momentum and the energy are conserved because they are simply exchanged between these two electrons. Therefore, the electron-electron scattering is a momentum-conserving scattering process, and it doesn't influence mobility of the bulk semiconductors. So it's quite difficult to observe this kind of scattering process. However, this can be observed and can be applied to the electron devices if this inequality is satisfied. Here, the LEE is the momentum conserving electron scattering length. And also we have a competing momentum non-conserving scattering process, such as impurity, surface roughness, and the phonon scattering. And we denote the scattering length of them, LMN. Another important parameter is the device size. The hydrodynamic effect can be observed if the electron-electron scattering length is much shorter than the device size, and also the unwanted momentum non-conserving scattering length is larger than the device size. I'd like to also touch on the other conduction process. If, for example, both LEE and LMN are larger than the device size, then we should observe the ballistic transport. On the other hand, when the momentum non-conserving scattering length is shorter than the device size, then the transport becomes diffusive. And I'd like to summarize the scattering process in electronic circuit, electronic device in this diagram. Here, this axis corresponds to the momentum non-conserving scattering process scaled by the device size. This is simply, this is a good measure of the material purity. Here, we take the inverse of the LEE scaled by L, which roughly correspond to the electron density. And when LMN is quite small, irrespective of the electron density, we observe the diffusive transport of electrons. And the resistive circuits, including CMOS source and drain, correspond to this area. And also, when the material is quite pure or the device is highly scaled, and also the electron density is quite small, we observe the ballistic transport. And as you know that by scaling down the MOSFET, the channel, the electron conduction in the channel, the diffusive changed from the diffusive transport to the ballistic transport. Now you can see here the very large space, and this is a region where the hydrodynamic effect is dominant in electron transport. And this is a region that has not yet been explored towards the generation or development of a new energy efficient device. And what we have demonstrated is that these areas is also very promising for developing the energy efficient electronic devices. And the electron aspirator we have developed is just an example of that. Okay, so let me summarize and make some acknowledgement. They are the co-investigators of this research. Mr. Himmer-san, who performed a major part of the measurement, and the Moral Sensei and the Hori Sensei supported theoretically and experimentally, and Takashi Sensei of Hokkaido University and Fujiwara-san of NTT supports the device fabrication. So let me summarize my talk. We have developed the electron aspirator using the nanoscale silicon MOSFET. And significant point is that this is the first observation of the electron hydrodynamic effect in silicon. And this could be promising to breaking the fundamental limit of the MOSFET drivability, which I hope lead us to the nano hydroelectronics for low power circuits. This concludes my talk. Thank you very much for your attention. Okay, that's all.
Yeah, that was a very interesting talk, Professor Yukinori Ono.
Thank you very much.
Very neatly you have covered about the electron aspirator operation, and you've introduced us to the new domain, electro-hydrodynamics regime, where, as you said, our young team can work towards new nano silicon devices. So very, yeah, it was very interesting to listen to the aspirator concepts and how you get amplification without additional expenditure of power. And that was a very interesting concept. So I just wanted to, if any participants want to have a discussion, it's open to the participants for discussion. Any questions, any clarifications from the participants? Lakshmi Kumar, if no, shall we wind up?
Yes, madam. Yes, madam. We can go for next speaker. Yes, madam.
Okay. Once again, thank you, Professor Yukinori Yono. And very neatly you've introduced the device structure. It will be useful for the participants. I think we can look into the new regime of electron hydrodynamics, where the purity and the electron density regime you have shown, that will be very useful to target and work further. Thank you, Professor. Thank you.
Okay, thank you very much.
Thank you.
Thank you, Professor Ono. Madam, I will share the presentation now. Slide for introducing the theme lecture.
Yeah, I do.
I think, sir, Professor is available.
Okay. Okay.
We'll ask.
We'll start.
Professor Chang, are you ready? Professor Chang, can you hear us?
Yes.
Fine.
Yeah. Shall I?
One second. I'm just sharing the presentation slide. Yeah, madam, you can proceed.
Welcome to the second theme lecture talk to be delivered by Professor Edward E. Chang. So I had great privilege in welcoming you and introducing you to the participants. Professor Dr. Edward E. Chang received his BS degree from Material Science and Engineering, National Tsinghua University, Hsinchu, Taiwan, in the year 1977, and his PhD degree from Material Science and Engineering, University of Minnesota, in the year 1985. Dr. Chang was with Unisys Corporation, gallium arsenide component group, ICONN from 1985 to 1988, and ComSat Labs Microelectronics Group from 1988 to 1992. He worked on the gallium arsenide MMIC programs on both the groups. He joined National Chiao-Tung University, NCTU, Hsinchu, Taiwan in 1992. In 1994, he helped set up the first gallium arsenide MMIC production line in Taiwan and become the president of Hexaware, Taiwan in 1995. He returned to teaching position at NCTU in the year 1999. And Dr. Chang is currently the Dean of Research and Development and Professor of the Department of Material Science and Engineering and Department of Electrical Engineering and NCTU. He is also the Director of Diamond Lab and the Director, NCTU TSMC Research Center. His research interests include new device and process technologies for compound semiconductors, for wireless. Chang is a senior member and a distinguished lecturer of IEEE Electronic Device Society. Currently, his research activities include indium phosphide gallium arsenide-based compound materials and devices for wireless communication and sub-millimeter wave imaging application. Dr. Chang has received quite a few honors from Taiwan and abroad, including 2 times Outstanding Research Award and Distinguished Contribution for Technical Transfer to Industry, both from National Science Council. Distinguished Electrical Engineering Professor Award from Chinese Institute of Electrical Engineering. He is also Distinguished Lecturer of IEEE, Fellow of Taiwanese Material Society and Fellow of IEEE. I am greatly honored to introduce such a high-profile professor to this audience, and we welcome you, sir, to deliver your theme lecture.
Okay. Okay, thank you for the introduction. It's my honor to join this conference. Actually, this is the 5th time I joined the conference, and also NCTU is the event social organizer. Okay, so so I'm really happy to join this conference. And then my talk will be extremely high performance Indian gallium arsenide FinFET for next generation CMOS logic application. In the last talk, we heard a lot about the progress in silicon CMOS. And this talk will be focused on the gallium arsenide 3-5 device for CMOS application. So the material will be InGaAs, okay, the high mobility materials. And then we would present the FinFET device using the Indian gallium arsenide as the channel material for these CMOS applications. Okay, next.
Excuse me, sir. Can you just put it on the full screen mode?
We already.
Oh, thank you. I think it's still, you can.
Okay. It's okay now?
No, we are able to see your next slide as well.
Okay, next. So my talk will include introduction, and then I'll talk about key challenge, how to make an Indian gallium arsenide MOSFET. And then I present the Indian gallium arsenide FinFET with record performance. And then we add some negative capacitance to the Indian gallium arsenide FinFET to further promote, enhance the performance. And then I'll come to the conclusion. Okay. And
Sir, Professor Chung, so can you just keep it in view mode, this full view mode, this presentation?
Pardon?
Full screen mode. Full screen. Okay, is that okay now?
No, it is still, it is not in full screen mode. Maybe that right hand side box you can close. Yeah, now it is fine. It is fine.
It's fine. Okay.
There is down one screen. What is that icon is there? You can click on that. So you are able to see that 75% something is written. Left to that.
Can you see now?
Hello, can you see our screen now?
Or you can press F5. F5.
Function key F5.
Does it work now?
Yeah, click that. Click that slideshow. Yes. Yeah, down where you had kept earlier. Yeah, click it.
Okay.
Yeah, I think we need to wait.
So now we change the slides, and please check if the slides change, okay?
A slide changing is happening. You can. I think Lakshmi Kumar will.
I think with this you can proceed, sir. I think it is fine. It is fine.
Yeah. It's fine now? Okay.
It's fine.
Yeah, fine.
Okay. So for the new architecture for the MOS device, okay, we start with the planar FET, and then we go to ultra-thin body SOI FETs, and then the technology progress to FinFET, and then to get all around FETs. So the change evolution, including fully depleted devices, and just the show in the view graph. Okay. Next, yeah. And so in this work, we actually use InGaAs as the material, because InGaAs have much higher mobility than silicon that allow you to have a higher drip velocity and low electric field. So using this kind of 3-5 material, you can have higher speed with low energy consumption. And on the right-hand side, you can see the ion of the device of the in-gas at different gate lengths. And this ion is much higher than silicon-based material, which means it will have a higher speed when you use as a logical device. And for the in-gas material, MOSFET, people have tried many different kinds of configurations, and many follow the silicon technology with a different configuration. For example, the width of the FinFET keep on decreasing, and later on you can use like a tri-layer, and also the gate-all-around, okay, which is the technology evolution of the silicon FinFET. And here we just follow this and use in-gas as the channel materials. And the challenge of these three devices is the device scale is very small. And one of the possible problems is the surface, if the surface is rough due to the aging, okay, you have a lot of side damages, then the mobility of the device will be graded, and rough, you will have rough sidewall and surfaces. And one of the biggest challenges in the past for the 3.5 for most application is that 3.5 material and the capacitors have a lot of interface traps. Okay, so it means that if you use high K material, high K and 3.5 material, the interface have a lot of traps. Okay, so in this study we follow the silicon technology. We use high K material and with high band material, but again we have to solve the interface problem, and the oxide have some border trap, and the interface have many interface trap defects. Okay. Next, please. Next, please. Next, please.
Actually, here it is not changing, but here it is changing.
Oh.
If you're able to see the slide change.
Professor, if you have any issue, you can mail me the presentation, so I will project it.
Oh, you mean I just go ahead?
No,
You have a slide, right?
No, you have to mail me. Please mail the presentation to my email so that I can.
Okay.
So
We were able to see the slide change actually.
Can you see now?
Can you see it now? Okay.
Yes, we can see.
Okay, so we're talking about the high K and the 3.5. The interface have many problems. This including the interface trap density and also the border traps. And these will cause some generation and recombination and through the middle traps, and that will affect your VTH and also the border traps may tunneling into the semiconductors, and that also will affect your VTH. And so the solution to this is you need to have a high-K material with a very low interface traps. Okay, so the way of doing it in our site is using the plasma enhanced atomic layer depolation, ALD. So these technologies have low temperature depolation and very low defect densities and precise sequence control and excellent step coverage. And also it's very reproducible. And we were able to use this tool to do remote plasma treatment on the surface. So you can get very good DIT with good film quality. So this is the most capacitors with remote plasma enhanced ALD material. And in this case, we use aluminum nitride as the interface layers before we put the high-K material, in this case, aluminum oxide. So this is actually aluminum oxide, aluminum nitride, and ingot PMOS, okay? And you can see that using this kind of technology, with this kind of ALD interface, you can see the material, the device is fully inverted, fully conversion. And then, with no surface peeling. And you can see that the DIT is very low, either from the experiment or theory. Okay, we can, if the DIT range is 10 to 12, and which can be verified from experimental and also from theory. Okay. And again, to reduce the EOT, we move the material from aluminum oxide to harmonic oxide. So this is a harmonic oxide, aluminum nitride, Indian gallium arsenide MOSFET. And again, we have N-type and P-type MOSFET. And you can see that both have very fully inversion and with very low DIT, both for N-type and P-type. And there's no Fermi level pinning and very low leakage current. So this is, using this technology, you can achieve a good performance, very perfect MOSFET, okay, Indian gallium arsenide MOSFET, okay. And then to further reduce the EOT, we move to harmonic oxide, aluminum nitride. In this case, harmonic oxide is 3.6 nanometer, aluminum nitride is 1 nanometer. And we use this as the high-K material. And then after that, we do remote plasma gas treatment. Okay, in that one, we can improve the interface quality. So with aluminum nitride and ammonia plasma treatment, we can reach EOT 0.6. And we also try with aluminum nitride and nitrogen plasma treatment. And in this case, we can get EOT at about 0.48 with CET around 1.34. Okay, so that means you can use either aluminum oxide, aluminum nitride with the plasma, ammonia plasma treatment, or aluminum nitride with nitrogen plasma treatment. Both give you a very good results. And then the DIT for both cases is in 10 to 12 range. Okay, so it's sub-nanometer EOT high-K material and the very low DIT that we can achieve. And after that, we also do plasma treatment. Okay, the device is done, and then we do follow plasma treatment. And this one, you can see that we do the just compared to just harmonic oxide, okay, which is the white line, and again with aluminum nitride interface, which is a blue line, and with finally the ammonia remote ammonia gas treatment, and which is red line. You can see there that there's an increase of 58% of the current, okay, after treatment, because the surface, okay, is greatly improved, so your mobility is improved, okay. And then you can see that the off current is also reduced, okay, because the defect is reduced, and then the hysteresis is increased, okay. So overall, you increase on current, okay, which make your device move faster, and you have low of current, which is energy saving, and you reduce the hysteresis, so your BTS is more stable. Okay. So actually, all this is done because the interface shape and border shape is reduced. So this table gives the benchmark of our work compared to the one reported in literature. So we have lowest DIT and low border shapes too, MBT. So combined together, we get the lowest overall DIT and border shape density together. Okay. And this is the TM image of the interface. And you can see that the interface is very clear and no interdiffusion of the atomic atoms. Okay. And then you can see that from the SPS, use this kind of PLD treatment. And you can actually see the from the SPS, okay, all this oxide formation is reduced. Okay, aluminum oxide, indium oxide, gallium oxide is all native state is nothing, and the amount of oxide formation is greatly reduced. Okay, and another advantage of using is this. Yeah, with advantage this use aluminum nitride is aluminum nitride can reduce the oxygen diffuse into the in-gas, okay, in-gas. But so if oxygen diffuse in the in-gas, then you, because the charge it carry, so you have polarity, okay, within the two materials, okay. So there's a change in the band gap alignment and Fermi level. You have diffusion of the oxygen into the sulfide material, and because of this aluminum nitride layer, you prevent the diffusion of the oxygen ions into the indium gallium arsenide. Okay, and then other than the interface at the high K material, you can further improve the quality of the MOSFET by reducing the in-gas, the fin thickness. Okay, so if you reduce the fin dimension, actually you can see that there's a so-called quantum confinement. Okay, from the you can see that all the electron is confined to the center. Okay, and the number of electron is increased, and also because it's not on the border side, so the scattering is reduced. So overall, the electron density increased, okay, due to the reduce in the dimension, due to the quantum effect. And also electron have less scattering, and that give you a higher current, okay. Next one, okay. And try to maximize performance. We can use different configuration of the fin shape, and here use the triangle, we get the best performance. Okay. So the next one is to make the indium gallium arsenide FinFET, because we use this configuration and we use high K dielectrics, okay, which including the aluminum oxide or harmonic oxide, and then we use +1 treatment. And next one, okay, we can see that with the channel 50 nanometer, 20 nanometer, and highest 50 nanometer, and the EOT 2.2 nanometer, and using this aluminum oxide as the interface, you can see that the dBOR is 88 and current is very high, 1.85 milliamp per micron, and then you can bias 2.5 volt. Your substrate slope is about 120 millivolt per decade, and GM is quite high, it's 2.28 millisiemens per micron. Okay, so from the right hand side, you can see that the current is quite high and the GM is quite high for this FinFET device. If we use sulfide material with proper oxide dielectric only as the dielectric material. Okay. And you can also see that this kind of FinFET device, even you scale your dimension to like a 40 nanometer, you can see that the DBO keep the same, and also the SS is not much change, okay? And VTH remain the same. So it's quite immune to the short channel effect. You can reduce the gate length, but your VTH, your SS, DBO is not much affected, okay? So the next one is the benchmark of this kind of Indian gallium arsenide FinFET compared to the reported silicon device. On the left-hand side, you can see the configuration is 20 nanometer device, and then you can nanometer thin, okay, and EOT is about 2.2 the device. And then you can see on the right-hand side is the fin width and GM, okay, and you can see on the right-hand side is a 3.5 in-gas FinFET. On the left-hand side is silicon FinFET, okay. And in the red dot is our work with the aspect ratio of 2.5, and we can see that the GM is around 2.5, okay, millisieverts per micron. So it's very good, okay. But okay, we can follow improved, okay. So what we do is we follow reduce the fin width, and then we follow reduce the EOT over dielectric materials, okay. So when you move to the next one with the hafnium oxide as a gate material, okay. So this basically the same as what we did in the last view graph, except that we change the aluminum oxide to hafnium oxide. So and also after the deposition of the film, you also do nitrogen post deposition treatment. Okay, so in this case, you can reduce the interface chip density in the border chips. So this in-gas Indian 53% FinFET with the channel 50 nanometer and fin with 6 nanometer, EOT 0.52 nanometer, you can get a very high current. ION is around 3.25 milliamp per micron, and also that's at 1 volt bias. But if you reduce to 0.7 volt, it still remains 1.98 milliamp per micron. And the GM is very high, like a 38 per millisiemens per micron at VDS 0.2, reduced to 0.5. Okay, and on the left-hand side, we can see that when the VDS is reduced to 0.5, the SS is still 1.69 millivolt per decade, and GM is like 38, 3.8 millisiemens per micron. Okay, so this is a very good performance, and probably is the best up to now. Okay, if you talking about the Indian gallium arsenide FinFET. Okay, this is Indian gallium arsenide FinFET with a 0.5 volt. Okay, usually silicon is 1 volt. Okay, so with the reduced bias voltage, that means we save more energy, but we still get very high on current. That means the speed is even much higher. Okay, and the GM is really high. Okay, so for this device, we present with the EOT 2.2 and the surface treatment. We use the high K we use. Actually, our device outperform both in-gas and silicon FinFET in terms of the current and also the bias voltage. Okay, and SS and the DBO remains very low. Okay, so this is a benchmark of the FinFET device we have with the VDS only 0.5 volt. And you can see that in this view graph, is outperform all the devices, including silicon and including 3.5s. Okay, so this is the highest report on devices. And And also for FinFET, this red card ion per fin, okay, for this kind of FinFET devices. Okay. And you can see that this is a record high GM and Q factor. Q factor means GM divided by SS, okay, for 3.5 device. And this one, okay, in this table, you can from the benchmark, our device outperform all the other devices, including planar device, FinFET device, silicon devices, and 3.5 devices. Okay. Okay, so far I have presented the best fin device, and next one is how we can improve it. Okay, the way to improve it is
Professor Chang, you have another 2 to 3 minutes to wind up.
Okay, sure, no problem. So we further improve by using ferroelectric, so you can reduce the SS, okay, because the ferroelectric changes your surface potential. So you can apply a low voltage, you still create a big potential on the surface. So we can get a very sharp SS, and that means you can bias at low voltage with high current. Okay, so the next one, okay, this is the ferroelectric we use, okay, half-linear nickel oxide. And next one, it shows the device, in-gas device with the nickel oxide, okay, as the dielectric ferroelectric material. And you can see that the current is improved, and also the most important is SS is reduced, okay, to very low, okay, as you can see in the figure. It's like in linear region 30 millivolt, in saturation region is 30 volt, okay, 30 millivolt per decade. So you can see that either in linear or in saturation, you get very sharp SS, okay, and some hysteresis, okay, of course. And then this is change conduction characteristics. You can see the transition at the ferroelectric start work. That means the NC start work, you can get very high GM. Okay. So the next two is the same, okay, which give you the same logic, but we have a MOSFET, and we also have FinFET with this kind of NC material you put in there. You can get very high sharp SS with like a 10 millivolt per decade type of things. Okay, but of course there's still something has to be improved. Okay, for example, the hysteresis. Okay, so okay, this is the benchmark of the 3.5 NC FET, and you can see that the SS is very low. Okay, it's below around 20 millivolt per decade. Okay. And okay, finally, okay, this is the in-gas, okay, FinFET, okay, and again, use the same approach, okay, and we can again get very steep SS, okay, so you can see from the figure is the SS is like 20 something, 24 and 23 millivolt per decade at the linear and saturation region. Okay, okay, next one. Okay, so I just skip it to the conclusion. So in the talk, we have demonstrated the in-gas FinFET with a channel at 50 nanometer and use plasma enhanced ALD treatment. Okay, and this device after treatment and proper high K material, you can get record high ion and record high GM and Q. Okay, so that means the way the material we choose and the process we choose actually is very effective. Okay, to achieve the best performance. Okay, and then the next thing in this topic is that we use NC material, which is ferroelectric material, and we have demo the in-gas with the substrate slope SS below 6 nanometer per decade. And this is the first time people demo this 3.5 use this NC FET showing very low SS. And these two technologies are promission for next generation high performance ultra low power logical applications. Okay, thank you. That's my conclude my talk. Yes.
Thank you, Professor Chang, for that interesting talk on in-gas MOSFET in comparison with in-gas FinFET, and very neatly you have briefly you have introduced to us the benefits of plasma enhanced atomic layer deposition and the introduction of high K material along with introduction of interface of aluminum nitrate with ammonia plasma and the benefits and how the immunity to short channel effects all were very interesting, and thanks for sharing your research results with us. And unfortunately, due to lack of time, we were not able to listen to your negative capacitance concepts in detail. Thank you, Professor, for your time.
Okay, thank you.
Thank you. Any participants? Thank you. Any participants would like to discuss or any clarification?
Madam, they can type in chat box also if they have any questions.
Yeah, participants, you can type your questions in chat box. Okay. I think there are no questions for Professor Chang. Once again, I thank you for your time and very interesting thoughts on Indian gallium FinFETs and the effects of fin shape and other details. Thank you, sir.
Thank you. Thank you.
Thank you.
Thank you very much. Thank you.
Can we check whether speakers are available now? Contributory lectures.
Yeah, sure.
Okay, can I read the names, madam, or can I show the presentation? I think Arun
Shall
Kumar.
we check?
Yeah, Arun Kumar.
Yeah.
Arun Kumar from Amrita Biosensor Research Lab.
Yes, sir. Hello, sir. Am I audible?
Fine.
Yeah.
And Murtaja Bohra, Mahindra University. Murtaja Bohra. Or anyone representing that paper, deducing uniaxial anisotropy for various NICR nanostructures.
We can call next.
Mahindra University. Okay, the third speaker is Vijay Srinivasan Murugesan. So he is from University of Tokyo.
Hello, sir. I'm Vijay Srinivasan.
Fine. Madam, two speakers are available, so we will go with the first one. Dr. Mr. Arun Kumar, P. Arun Kumar.
Sir?
Yeah, you can share the presentation now. Arun Kumar, I would like to remind you.
Yes,
so
sir.
in 6th minute we will give a reminder.
Okay, sir.
And after that, in 2 minutes you have to complete your presentation. And last 2 minutes, I mean of the 10 upon 10 minutes, 2 minutes will be for the discussion. Okay.
Okay, sir. Thank you, sir.
So please leave 2 minutes for the participants to discuss your lecture. Okay. So please try to complete in 8 minutes. Thank you.
Thank you, sir.
Yeah.
Is the slides visible, sir?
Yes.
Are they changing, sir?
Yeah,
Yes.
fine. You go ahead.
Thank you, sir. Greeting to one and all. I am P. Arun Kumar from Biosensor Research Lab in Amrita University, Coimbatore, India. My work is based on fabrication of point-of-care testing devices for chloride-ion sensing. One of the significant electrolytes in body fluids like blood, sweat, and urine is chloride ion. This ion maintains pH balance, electrolyte balance, and many significant bodily functions. The chloride ion imbalance in blood leads to several conditions like dyschloremia, etc. And the chloride ion imbalance in sweat is the gold standard for detection of cystic fibrosis. Cystic fibrosis is a genetic disorder affected various organs, especially the lungs, liver, gallbladder, and is one among the leading cause of death among children. Early diagnosis and treatment is important in improving the survival rate and life expectancy of the patients. The detection of chloride ions is also helpful in monitoring the metabolism rate of athletes. The objective of my work is electrochemical detection of chloride ions in body fluids, especially by point-of-care testing devices. For this purpose, I have synthesized an electrocatalyst with graphene oxide, silver, and manganese. To the graphene oxide suspension, I have added silver nitrate, manganese sulfate, and urea and allowed it to react for 24 hours at 100 degrees Celsius. After that, they were purified and dried to get silver manganese modified graphene oxide electrocatalyst. This scalable urea hydrolysis method of synthesis will help in mass production of the electrocatalyst that may further helpful in commercial application of this sensor. To test the electroactive nature of this catalyst, they were screen printed onto a 3-electrode system, which is printed on a flexible, disposable, and miniaturized platform using conductive inks. This conductive inks is one method of immobilization, and it is greatly helpful in commercialization in comparison with other methods like drop casting method or electrodeposition. The advantages of screen printing also include it is a highly scalable method, it is highly repeatable, and the precision is much higher than other manual methods. The design of the electrodes can be suited according to our needs, and this custom-made screens is very helpful in terms of different applications. For characterization, XRD reveals the presence of both carbon, silver, and manganese species present in the synthesized sample. And we can see that a bare screen printed electrode and a screen printed electrode coated with the prepared catalyst in the AFM images. The increased roughness for the sensor electrode with the catalyst coated material is one among the reasons for increased electroactive nature of the sensor. In electrochemical characterization, the fabricated sensor was tested in sodium nitrate medium with and without the presence of chloride ion. It can be seen that the bare electrode, that is without the catalyst, there is not much current response in comparison with that of the catalyst coated with our material. The impedance spectroscopy also agrees with the discussion. And it can be seen that Faraday peak was recorded near 0.1 volt for the catalyst coated electrode in the presence of chloride ion. This is due to the conversion of silver species in the catalyst to silver chloride in the presence of chloride ions when the sample was introduced. This shows that the catalyst ink is electroactive towards chloride ion. For quantification of the response, the technique called differential pulse voltammetric is utilized, and we can be seen that a linear response was observed for a range up to 40 millimolar. Then the electrode was tested for interference and real sample analysis. It can be seen that even in the presence of common interfering molecules, the synthesized catalyst was selective towards only the chloride ions. They are also tested with simulated switch sample prepared in a reference to the work by Harvey et al. And this proves as a proof of concept that the real-time application of the sensor is made possible. In order for fabrication of a point-of-care testing devices, this procedure of fabrication was optimized. First, the base electrode, which was printed by screen printing technology, is kept as the foundation of the sensor. Above that, the electrolyte which need to be tested was incorporated onto a cellulose membrane. It is done so that no other external introduction other than the sample should be made. Other than that, we have a highly hydrophilic membrane in order to wick the sample on introduction into the working area and for uniform distribution, which will further increase the repeatable nature of the sensor. And finally, we have an adhesive sticker. It is used to wrap and seal all the components together, and it is form a point-of-care testing prototype. And this prototype is tested with different chloride ions prepared, and we can be seen that in a range of 0 to 40 millimolar, we are seeing a linear increase in current response, and the sensitivity of the highly fabricated sensor is 30 microamps per millimolar per centimeter square. The fabricated prototype is also tested with serum samples and diluted serum samples with spiked chloride concentration as well. This also falls in the range of the fabricated sensor's response. In conclusion, material for electrochemical detection of the chloride ions was synthesized. A scalable sensing technology was utilized for screen printing and in synthesis. The real sample analysis in simulated sweat and serum showed that the real-time application of the sensor is possible, and a fabrication procedure was optimized with each components to increase the scalability, increase the sensitivity of the sensor. The scalable, affordable, accessible, and non-enzymatic point of tension strip is highly possible towards a commercial product. The future scope is that this can also be fabricated on a paper substrate, and they can be also used as a wearable sensor for chloride ion detection towards cystic fibrosis diagnosis. The sensor can also be integrated with a handheld meter for real-time application for on-site testing. I'd like to thank DST for the fund provided in order to carry out this work. I sincerely thank the Center of Advanced Characterization in Amrita Vishwavidyapitham for the help in the study of the material. I also thank ICONN-2021 SRM University for the opportunity provided to present my work. Thank you.
Thank you, Mr. Arun Kumar. Participants, any questions? Open for discussion. You can post your questions in the chat box.
Madam, for the second presentation, one co-author is available, so he is going to present.
Okay.
I think Sai Vittal. Sai Vittal, you can share the screen now.
Yeah, we'll question Arun Kumar. There's no question session. Can we?
Is my screen visible?
Vittal, can you wait for just 1 minute? Because we are waiting for any question from the participants for the previous presentation.
Okay, fine.
Any questions for Mr. Arun Kumar? Yeah, I would like to have a clarification. What is the range of chloride ions in serum and sweat?
In sweat, it is usually around 140 millimolar, and in serum, it is usually in the range of 95 to 100 now.
What is the range of concentration you have studied in your prototype?
In my prototype, I've studied from 0 to 40 millimolar now. So we have to dilute the sample before introduction.
You have not pointed out that, right? Okay. What is the dimension of the electrode final prototype?
The prototype electrode has a dimension of 5 millimolar cross 30 millimolar now. But the working area is only 5 millimolar cross 7 millimolar now.
I'm asking the dimension of the electrode.
The working area is 2 millimeter in diameter now.
What is the sample size required?
Ma'am, sorry, ma'am.
What is the sample size?
Sample size is 20 microliter will be enough. Sample volume 20 microliter will be enough.
20
microliter.
Okay, right. And that needs to be diluted, and then you do the calibration.
After dilution, 20 microliter is enough.
Okay. What is the novelty you claim in your work?
Novelty is this fabrication of the prototype is itself novel. We have several works on how to do this works, but in order for the fabrication of an actual prototype and the movement of them more towards a commercial product is solving step by step, moving towards the final product now available in the market.
Okay, thank you.
Thank you, ma'am.
That was a nice presentation. Thank you.
Thank you, ma'am.
Can we have the next presenter share the screen? Vittal?
Yes, ma'am.
Yeah, I think the 6th minute you'll get a call. You can have 2 minutes for winding up. Last 2 minutes for discussion. Totally 10 minutes. Your time starts.
Is my screen visible?
Yeah, visible.
Yeah, I'm starting. So good afternoon, everyone. I am Vittal. I am an undergrad student in electrical and electronics at Mahindra Eco-Centric. So today I'm really excited to be presenting as it is indeed my first conference. So today our contribution involves around deducing uniaxial anisotropy for various nickel chromium nanostructures. And I have been working under the guidance of my professor, Murtaza Bora. So let's start the presentation. Why is a study necessary? It is essential because these structures find a good application in cancer treatment because we can calibrate the Curie temperature to a few degrees above body temperature by appropriate chromium doping. They also have several direct industrial applications. But keeping the bright side aside, to this day, very few studies have been reported on the structural correlation and magnetic properties of these nanoparticles. Therefore, it became necessary to scrutinize their structural magnetic correlation at the nanoscale level. And also, the other few studies reported didn't take interaction effects into account. So in this study, we used a phenomenological model that takes interaction effects into account. So these are the samples which we synthesized using a magnetron sputtering system on silicon substrates. The samples are nickel nanoclusters, nickel chromium 5% nanoclusters, and nanoclusters annealed at 450 degrees Celsius and vacuum, nanogranular thin film with a deposition time adjusted at around 3 minutes. And finally, nickel chromium Ag nanocomposite with 65% Ag and 35% chromium with deposition time adjusted at around 10 minutes. So what did we actually do? We have adopted the random anisotropy model that includes interaction effects into account, and we imposed our experimental blocking temperature versus magnetic field data onto that model. This below equation is based on studies reported for non-interacting models. Here, Ku is the uniaxial anisotropy. From RAM, we can conclude with the following equations for effective anisotropy and effective volume. Here, N is the number of correlated particles that is defined by the below equation, and D is the diameter of the sample particle, and L is its corresponding correlation length. Here, X is the occupation percent in the structure matrix. Then, using the interaction intensity, we deduce the following equation for the correlation length as the function of H. Now, we substitute all these into the non-interacting model to derive an equation that is purely based on coupled interacting particle model. Using the above derived equation, we our data with the following experimental parameters and establish the value of the uniaxial anisotropy for all our values. In fitting, we use certain machine learning to re-verify whether our final indeed replicate our original data. So now, before talking about the final results, I would like to mention that we also measured several magnetic components of our samples at above and below blocking temperatures. Here, MH data was utilized and SPM, FM, and PM equations were carefully studied by referring various other papers. For SPM, we have used the Langevin function, which is defined as follows. Then for FM, we have made use of this following equation, and for PM, we made use of this simple linear equation. So here I'm showcasing MH fittings only for one sample, nickel chromium 5% nanocluster, since I don't have much time. According to theory, SPM would likely contribute more for data above the blocking temperatures. But to increase accuracy in our study, we added PM contribution as well. The following SPM plus PM equation was used, and this resulted in a good fit that is showcased on the right. Now, for below blocking temperatures, since there is more coercivity, we can theorize that FM contribution is dominant. But since there would also be SPM contribution in minimal amount, we utilized SPM plus FM here and carried out the fit, which is showcased on the right side. This fit actually assured that our theory was on a good basis. And finally, these are the results that I conclude on. Beta is the SPM contribution for below blocking temperatures, and 1 minus beta would give us FM contribution. Other terms apart from Ku are self-explanatory. The values for Ku lie in the range of the attributed value for bulk Ni, which is 1.5 into 10 power 5 joule per meter cube. This ensures that our research model and values obtained are reasonable. From this validation, it can be concluded that nickel chromium Ag nanocomposite has the highest Ku among the nanostructures due to its Ag hybridization. It is also observed that more is the surface segregation, more is the value of Ku. This property is clearly evident from the results and exhibits the reason why nickel chromium 5% has a higher value compared to its annealed nanocluster counterpart, followed by the nickel chromium 5% nanogranular film. For nickel nanoclusters, it is concluded that it has less segregation than bulk Ni and therefore has a lesser value than the bulk. So yeah, this is the end of my presentation. I would like to acknowledge my professor Murtaza Bora, SRM and ICON for letting me present at my first conference. I'm really glad to be part of this community. Thank you.
Thank you, Mr. Vittal, for your presentation. Open for discussion, participants. Any questions from participants? Yeah, can you tell me what do you mean by blocking temperature?
It is the temperature below which, ma'am, SPM, like magnetic, cease to exist. I mean, like it can't flip anymore. So
what is the value for this material which you study, nanostructure which you study?
These are the 5 samples. What I mean, like the initial answer.
Pardon?
No, like what value do you mean? Like the anisotropy value?
Yeah. Mm.
Yeah, here they are. So these are the values, like in this table. The
Your
first
screen is
second
not
column.
visible. Your screen is not visible.
Okay, one. Okay. Now is it visible, ma'am?
Yeah, it's visible.
Yeah. So the second column are the values of the samples, like Ku values.
Okay. So you said you're studying uniaxial anisotropy. How did you justify it? Uniaxial anisotropicity?
Yeah, so I mean, justification, like we just took the raw image data and figured out, the TB versus H data and just like
Go back to your title.
deduce the, yeah, one.
Title slide. Yeah. Deducing uniaxial anisotropy, you said. So how did you deduce it?
Yeah, so we used the TB versus H data from our experiments, and then we used the random anisotropy model. I mean, we imposed our data into that equation and we carried out fittings. From that, we the Ku parameters. So like that, we deduced. So like we considered interaction effects.
You said it will be useful for cancer and other applications. Can you really link to one application, real-time application?
Yeah, I mean, like we can target cells. So like we can calibrate to a certain temperature and
statement which you're talking. Can you just target more, be more specific in, because you very specifically said the need for the study. So what is the need for the study? What is the innovation?
I mean, they also have, they also have good applications in magnetic devices and magnetic fluids. Like
I just
read about them, but
having taken up a research in one, you should know that you uttered that this is a need for the work. Be specific in the application. Fine. Okay. Target an application and we can proceed. And what is the innovation? NICR nanostructures not at all available. Nickel chromium
yeah,
structure
very
available.
few reports are. No, I mean like when we went through the papers, like very few studies were reported on them. So
What is the additional findings from your end on this?
yeah, we found out the each individual KU values and the beta values, like the contribution of SPM and FM per our data. So yeah, those are the ones which we found out.
Any questions, Professor Lakshmi Kumar, from your end?
Madam, I have a simple question. Sai Vittal, I would like to know
Yes,
what do you mean by uniaxial anisotropy? How it is different from anisotropy?
yeah. So like when like uh, when a substance is like getting magnetized in an easy axis, so that is defined as uniaxial. Like that easy axis is nothing but uniaxial one. I'm not considering about the effective anisotropy, only anisotropy on one axis, the easy axis.
No, that is how we define anisotropy and isotropy, right? In one direction only, generally, right? But
Yeah, but
why you have added uniaxial the word?
Like effective includes I
Yeah,
mean,
I see.
effective includes for all the correlated particles.
I remember anisotropy means changing properties in one direction, right? If the properties keep
Yeah.
changing in one direction, that is called anisotropy. But what do you mean by uniaxial anisotropy? Is there any special meaning for that?
Like as far as I remember, when I mean, for one of our sample we took only z-axis. We considered like how it's how the magnetic properties are varying when we magnetize it only through the z-axis.
I think that is what anisotropy meaning.
Yeah, but
what is
like,
meant by uniaxial?
Yeah, I mean, like anisotropy itself is like, I mean, meaning is one directional, but like, I mean, uniaxial means we reported only on one magnitude, I mean, only one axis, like, so that's what I.
Okay, please kindly check on that, okay?
Yeah, sure.
Yeah. Thank you, Sai Vittal. Can we go have next speaker?
Yeah, next speaker is Vijay Srinivasan Murugesan. So he's from University of Tokyo. Vijay Murugesan.
Hello, sir.
Yeah, you can share your presentation now, okay?
Just a minute. Good morning to everyone. Today I am going to discuss. Just a minute.
A call at 6th minute. Additional 2 more minutes. Last 2 minutes for.
Okay.
Can start. Your screen is visible. You're audible.
Okay. Thank you. My research topic is focus on fabrication of high performance mixed cation halide perovskite solar cell by post vapor annealing. Why perovskite used as the light RS in the solar cell? Because the perovskite has a very good absorption coefficient. It has we can tune the optical band gap by optimization of the molar ratio of the cation and halide, and it has a higher charge carrier mobility, and the result is show highest efficiency around 25% in the past decades. In the DACC, dye is a absorbing material, but in this dye does not absorb all the light, and result efficiency is lower. And Miyasaka from Tokyo, Japan, he first used replace dye with the perovskite, and he achieved the efficiency around 3.5%, and the efficiency is improved from 6.5 from Nanju Park, South Korean professor, by increasing the concentration of the perovskite. Then from the Oxford University, they're changing the liquid electrolyte by solid whole transfer layer, and they achieved a 10% efficiency. Then the result increased from 10% to 25% by changing the mixed cation halide by the composition and as well as surface fashion. So how to boost the efficiency of the perovskite? In this, first we need to understanding the photophysical properties of perovskite as well as the electron and hole transport layer, as well as we need to understand the band gap alignment and how to align the band gap align the perovskite band gap with respect to electron and hole transport layer, as well as we need to understand about the charge transfer mechanism. Finally, getting the good quality perovskite also important for the boost efficiency. Among this, the quality of the perovskite is very good thing. One of the main key factors to get a high efficiency, because it has larger crystals, reduce the recombination of the ground boundaries, result reduce the bulk defect as well as increase the efficiency of the solar cell. Now, how to get the larger perovskite solar cell? Means perovskite crystal. There is so many method available, like hard casting, solvent vapor annealing, and anti-solvent dripping method. So my work focus on fabrication of the high performance cesium based mixed cation halide perovskite solar cell using solvent vapor annealing method. Here I fabricated the solar cell with the following structure. Here the TiO2 and the mesoporous TiO2 used as a electron transfer layer. The cesium MAFA PB halide used as a light absorber, and this molar ratio of the perovskite was optimized by this one, and this one give the higher efficiency as well as very good thermal stability. Further, we need to increase the efficiency of this solar cell. We need to increase the perovskite crystal by asphalt ripening using the solvent vapor annealing method. This will be improve the perovskite crystal size. This when increase the perovskite crystal, it will there is a good connection between the TiO2 and the perovskite. Next, I am discussed about the fabrication of the device. Here, the device structure fabrication is mainly four part. One is the ETL part, electron transfer layer. Next one is the active layer, and this one is the hole transport layer. Finally, this is the counter electrode. Here, the first TiO2 compact layer was sprayed by spraying technique by and heated at 500 degree. Then mesoporous TiO2 was coated by spin coating technique. Then it was annealed around 500 degree. Then lithium was doped into the doped, and it was annealed 450 degree for 20 minutes. The next, the main important light absorber was coated, and this after spin coating the perovskite, we need to anneal by hot plate. When heating the perovskite film, we need to cover the watch glass immediately. It will slow down the evaporation of the solvent. Then it will when slow evaporation, asphalt ripening occur, result the larger perovskite crystal was we get. The larger perovskite grain was getting in the two step. One is like slow evaporation, and the second thing, there is a moisture accumulation in the grain boundaries, small grain boundaries. Both these two can merge the small grain, you will get the larger grain. Then after that, we coated the whole transport layer Spiro OMETAD. Then finally, counter electrode gold was coated. This is a solar cell device one. This active area of the cell is 25 mm square. This one is a SEM image of the top surface of the film, perovskite film. This SVA annealed device shows larger crystal size compared with the non-USE method. This have decreased the grain boundaries compared with the non-SVA, and there is a here we can see some disconnect grains there, and but in the case of SVA we cannot see this kind of disconnect grain. When we check the cross section, the perovskite forming a monolithic layer, and there is very good connection between the TiO2. This one is the TiO2 layer for ETL. This one is a whole transport layer. This one is a counter. We can this is completely merged with the this both TiO2 as well as pyro. Where in the case of non-SVA method, there is we can see the grain is very small grain. We can see some disconnected grains. When we check the XRD analysis for this sample, and this sample shows that SVA device show more intense peak compared with the non-SVA. This means increased crystallinity. The inset peak for this one shows the characteristic peak of 110 of the perovskite. This SVA shows more intense peak compared to the non-SVA, like more crystallinity. The better crystallinity good we'll expect to improve the efficiency. Next we can see the photovoltaic character of the device fabricated SVA and non-SVA method. This is a JV curve. Like here you can see the red one. Red one is like a SVA annealed photo device, and this blue one is like non-SVA device. Here the SVA like a solid annealed one shows higher efficiency compared with the non-SVA method. The improvement of efficiency because of the difference in the JSC. The higher the JSC in SVA due to larger crystallinity. The larger crystallinity reduction in the recombination in the grain body.
Vijay, you have 2 more minutes to wind up.
Okay, ma'am. Further, the VOC and fill factor is slightly improved. And next one is like IPC spectra. This one is IPC spectra of the corresponding IV curve, and this this IPC also like a value also slightly higher when compared to non-SVA. And for the integrated JC value is a good agreement between observed this one. So we will get some good result. Further, the main thing, one more thing here we can see there is a very small hysteresis between means there is small gap between this SVA device, whereas in the non-SVA device we can get the large gap. This is also some advantage of this method. From the summary, we can conclude that like SVA method device shows larger grain with ultra smooth perovskite film with high crystallinity. Larger the crystal shows reduce the surface boundary and promote the connectivity between the adjacent perovskite grain. This suppresses charge recombination between the adjacent layer like perovskite as well as ETL and HTL. From this we can from this when decreasing the surface recombination, like efficiency is improved like from 20% and negligible photoconductivity compared with the non-SVA method. And also this SVA method producing with a high reproducibility compared with the non-SVA method. And based on this, this PVA method can be applied to enhance the perovskite film quality regardless of any fabrication method. And I would like to thank Miyasaka and Shigawa lab member. He is Professor Miyasaka and he is Professor Shigawa. And thanks for the financial support from the NERO. And thank you for the kind attention. Thank you.
Thank you, Dr. Vijay, for your presentation. It's open for discussion now. Any questions from the participants?
No, I have a small question. Probably I would like to know from the speaker. So what makes actually perovskite materials for giving more performance as a solar cell? It seems that you are using some method for the perovskite solar material.
Yeah.
For improving the efficiency. Actually, basically, what makes perovskite to show more performance or more efficient than normal semiconductor something?
Actually, solar cell device maker. Here, generally, people use like a single cation based perovskite. This result shows generally around below 15 or 16 or something like that.
No, it
but
is
when
like
you use,
Murugesh, just I want to know in a simple way whether, like, the photon absorbing capacity will increase or the conductivity will increase when you use perovskite compared to normal semiconductor.
Okay. Because it's very good light harvester as well as a very good charge carrier mobility. This two is main thing actually.
So mobility will increase.
Yes, mobility will increase.
Okay. Thank you.
Dr. Vijay, I have one question.
Yes, ma'am.
The thing is, nowadays, whatever you do in perovskite, you will find that somebody else has already done that. And I can see that this solvent vapor annealing, people have done this method long back. So I have a question that what is the novelty in your work?
Ma'am, actually, this SVA method already done some other perovskite, but in my case, like the optimizing this molar ratio and this like thickness of this two layer is more important. Generally, this kind of high efficiency perovskite solar cell made in the glow box, but I made this device in the ambient air like a 20% humidity controlled room. So this one is a major reason. Main reason. Further, along with we are increasing the crystallinity by increasing. We get some more efficiency, but this one is a major thing actually. Mixed cation with the optimistic condition. This molar ratio is very important actually. This solvent vapor annealing already existing one. Just you applied this one, but this one is a main thing, man.
Okay. Have you worked with Professor Miyasaka's group?
Yes, ma'am.
Okay.
Okay, Dr. Vijay, that was a nice presentation. And as I think
thank you, ma'am.
Dr. Lakshmi Kumar, can I?
Yes, madam. So we have come to the end of the session 6C. So on behalf of the organizing committee, I thank Professor Shanti Prince for chairing the session and conducted the session in a very smooth way. So it is going to close in time without any further delay. So I also thank the invited speaker, Professor Ono, and the speaker who has delivered the theme lecture, Professor Edward Chang. And also I thank all the participants, and I thank the speakers, Arun Kumar, Sai Vittal, and Vijay Srinivas Murugesan for their excellent presentations. So finally, I thank each and every one who attended this session and made it successful. So thank you very much. Thank you once again. Shanti ma'am, thank you very much.
Yeah, thank you. Thank you all for the participation. It was a good session. We enjoyed the session for your contributions and sharing your research with us. Thank you. Thank you all.
Thank you very much.
Thank you, sir.
I think we can leave the session now. We can
Yes,
join the next session. Yeah, thank you.